Okay, so today I want to have a quick look at how to calculate the skin friction for a lattice Boltzmann solution. So I've read in here a VTK file from my flow solution over a sphere, and in this flow solution I've got distance field, I've got the eddy viscosity, density and velocity, and they're all in lattice Boltzmann units. So for example, the velocity is 0.04. So in order to calculate the skin friction, I need to get the velocity gradients. So the first thing I'm going to do, and the quickest way to do it, is to first do cell data to point data. And it's best to do this first and then calculate the velocity gradients. Because if you do it the other way around, it can take quite a bit longer. So that's interpolated onto the point data. And next I need to select gradient of unstructured data set. So that'll take a while to do that. By default, it's done the distance field. So you just need to select the velocities and that will calculate your velocity gradients. And also down here, it will calculate vorticity and Q criteria, which I've only just noticed. So now I should have my velocity gradients. So if I do like an outline of the surface, I can see I've got gradients there. In theory, I can view the gradients. So there's not much going on the outside. But I want to look at the surface. So I'm going to do a contour plot of my surface and select distance field. So that's a contour of the distance field. So now I'm looking at gradients on the surface. So what I want to do next is a calculator function in order to calculate the shear stress. So calculator function, I'm just going to put this down as force or X force. So I'm looking for the X component of the shear stresses. And I've done this before, so I know what the function is. Tau W equals mu t times velocity gradient. That's essentially what we're calculating. But I want the shear stresses that are tangential to the surface, or rather, I want to look at is du by dn, which is the change in u velocity over the surface normal. And so the function that I'm going to use for that is this one. So I've got my surface normals here, surface normal components, and then velocity gradients here. And those velocity gradients are just du dx, du dy, du dz. So I'm just going to cut and paste that into my calculator function. And hopefully that will give me something. And so then I can select that. I know it's worked because I can select it there. And then I can have a look at the result there. And I can have a look at the scale of that, for example. So now I've got my shear stresses on the surface. I want to integrate that. So the last step is to integrate variables. And integrating that variable, if I look at the X force, there's just one result there. And that's 0.00272. It's negative. I think that's just a sign convention issue, but it's the drag force due to the shear stresses on the surface. So that's how you get the forces out, your viscous forces out. So having got that number, skin friction is the X force, which is 0.00272. I've already calculated half rho v squared and the area. The area in this case is the surface area of the sphere, which is 4 pi r squared. Because the radius is a half, that's equal to pi. And I've done a quick check of the integration that when I set the calculator function to 1, then it gives me the total integral is 3.12, which is very close to 3.14. So that's just checking that the surface area of the sphere is equal to pi. And so I've got a force here. This is the force that I've integrated, that I've got by integration. Then that needs normalizing by half rho v squared times area, which comes out at 0.002. So they're similar numbers. And so that gives a skin friction drag coefficient of 1.088, which is very high. It's much higher than it should be, much higher than we're expecting. So I believe the calculation procedure is correct, but I think that for a combination of reasons, probably because I'm using the bounce back method, and probably because the mesh is too coarse, and probably because the turbulence values are quite high, that I'm getting quite a high value here. So if I use a different method from bounce back, like something like tangential wall flow, then I expect that this number will be a lot less. But for this flow solution, I think that this is the skin friction drag coefficient of 1.088. And when I use a similar method to calculate the pressure drag coefficient, I got 0.4, which is a lot more like you would expect. But yeah, so that's how we do it. And so just as a quick recap, you read in your flow solution from your lattice-Boltzmann result, do cell data to point data, then you calculate your gradients and make sure that you're calculating the gradient of velocity, otherwise it won't work. So we've got velocity gradients, and when you do that, it gives you all of your velocity gradient components. Do a contour plot of the distance field, so you need to have a distance field included in your solution. And then use a calculator function to calculate the normals times the gradients and multiply by the viscosity. And you integrate that over the surface to get your total X force. And just if you have a quick look at the calculator functions, you can see here you've got the surface normal components, and you've got your velocity gradient 0 through to 8. So that's all of your velocity gradients. So that's how it's done.